the fact that the Carnot engine has highest efficiency working between two temperature reservoirs gives rise to something called thermodynamic temperature. So, we are going to talk about that. So, remember that a Carnot engine working let us say between two temperature bath T1 and T2, where T1 is high temperature bath and T2 is the low temperature bath, and let us say it takes in Q1 amount of heat, does some work and throws away Q2 amount of heat. So, this particular engine will have, or you can will have the efficiency as 1 minus Q2 by Q1. So, where we know that Q1 is the heat that is taken in from high temperature and Q2 is heat that is thrown out to the low temperature. So, you see this efficiency eta, which is 1 minus Q2 by Q1, depends on these two temperatures T1 and T2, right. So, we can say that the efficiency is basically a function of two temperatures T1 and T2, because nothing else is required to define the efficiency of a Carnot engine apart from that the heat taken in and heat thrown to two different temperature reservoirs. So, we can call that this is particular efficiency some function, let us say phi 1 phi of T1 and T2. Okay. Now, let us construct another engine, a combined system where two engine works simultaneously. Heat Q1 is taken in from high temperature, some work is being done and Q3 is thrown to an intermediate temperature reservoir T3. So, T3 works as temperature reservoir, low temperature reservoir for the upper engine, let us call that A, and then same Q3 will be taken in by another engine called B, which does some other work, and finally Q2 heat is thrown to the T2 temperature reservoir. So, what we have done is that we have replaced one engine by two engines in and there is a temperature reservoir in between T1 and T2 temperature. Okay. Since the heat cannot escape, it takes in and gives the same amount of heat to the next engine. So, now this is a combined system. Now, if you calculate the efficiency of engine A, what you are going to get? 1 minus Q3 by Q1, and this one is a function of T1 and T3, right. Similarly, eta B, which is the efficiency of the second engine, is 1 minus Q2 by Q3. Therefore, we can say it is a function of T2. So, we are writing like first high and then low. So, T3 and T2. Okay. Okay. So, now you see, if I consider the final initial and final temperature differences, then efficiency of this engine, let us call it C. So, efficiency of engine C will be same as that of the combined efficiency of the right hand side engine. Okay. So, now if I rearrange a little bit here this particular equation, let us say from here if I rearrange a little bit, then what I get is that Q2 by Q1 is equal to 1 minus phi T1 T2. Okay. We can invert it and write Q1 by Q2. So, we are inverting just to say that heat input divided by heat output is 1 by 1 minus phi T1 and T2, right. It is still a function of T1 and T2. So, let us call it f T1 T2. Now, finally, what we got? We got for the engine C, we got Q1 by Q2 is equal to a function that is a function of T1 and T2. Okay. So, we can write the same thing for above two. So, from eta A we get heat input is Q1 by Q3 is a function of T1 and T3, and from eta B, the engine B, what we get? The input is Q3, output is Q2, we get F T3 T2. Now, you see one interesting thing happens. I can multiply equation 1 and equation 2. So, if I multiply equation 1 and equation 2, what I am going to get? Q1 by Q3 into Q3 by Q2 is equal to F T1 T3 multiplied by F T3 T2. Left hand side cancels and gives us Q1 by Q2 is equal to product of two functions. Okay. Now, this we get from here, let us call that equation 3, and we already have from this equation 4 Q1 by Q2. Now, 4 and 3 we can equate. So, what we have seen that from engine C we got Q1 by Q2 as a function of T1 T2, and from combined engine A and B we got Q1 by Q2 as F T1 T3 multiplied by T3 T2. Okay. So, equating these two we get T1 T2 is a product of T1 T3 F T3 T2. Now, you see somehow this product of these functions is dropping out here, even though we have introduced a temperature, and that is possible if this function T1 T2 or any two temperature is a ratio of function of these two temperatures separately. Let us say if I write in, I can show you. So, this can be a function of so psi T1 is a function of T1 and this ratio is the overall function. We can write the same way. You see, if we write that, the psi T3 cancels out. So, F is basically F, which is a function of two temperatures, is basically ratio of function of individual temperatures, right. So, now what we learned from here is that, and where did we get this? Now, what is our F T1 T2? Our F T1 T2 is nothing but Q1 by Q2, right, and we got F T1 T2 as psi of T1 by psi of T2. So, this is the basic formulations of the thermodynamics temperature. So, you see it is not exactly a temperature, it is a function of temperature, some function of temperature. Now, Kelvin used a linear function. We can use some linear function which changes with T1. Now, if you use a linear function, or we can call this psi T1 itself as T1, then we can say that the ratios of heat input output is related to the ratios of two thermodynamic temperatures. You only need one specific point in order to determine the other temperature. So, for example, if you calculate Q1 and Q2 for a known temperature, and the known temperature typically is taken to be the temperature of triple point of water, which is 273.16. So, this is T triple point is known, Q1 Q2 will be measured, and then you can get the value of T1. So, thus we can measure the temperature, given that we can calculate heat input and output. So, in real experiment, especially below 1 Kelvin temperature, where the gas, see other the temperature that we learned from zeroth law of thermodynamics is when we combine a property with the heat. So, for example, or with the temperature, for example, we say that how much is the value of PV when the pressure is very low, and how much is the value of PV with respect to PV at triple point. That will give us a measure of the temperature. that is in a gas thermometer. Similarly, for other cases for solids and other mercury, we calculate the property by looking at the changes in the volume or changes in the pressure and things like that. Here thermodynamics temperature, we are calculating the temperature by calculating the heat input and output, and that is possible because Carnot engine gives us that. Remember that for ideal cases we exactly know that Q1 by Q2, in ideal gases case we know that Q1 by Q2 is exactly as T1 by T2. That is from our normal temperature definition itself, it gives that in ideal gas. However, in general for non-ideal gases also we can write the ratios of heat input output as a function of the individual temperatures. Thus, Kelvin actually decided given this Kelvin scale, and one can see that when one of that will go to 0, then let us say in order for the efficiency to go to 1, the one of the temperature has to go to 0, and in that the heat output will be 0, there will be no heat going out. So, it becomes an adiabatic step itself. So, when the isothermal and adiabatic becomes equal, at that point your efficiency will become 1. Okay.